Firstly, thank you very much for the kind invitation for us to present at this this webinar, and at all for that fantastic sort of pitch up to where we are. I'm maybe going to, at risk of repeating some of the words that you just mentioned, I'm just going to dive in by a bit of context setting. So, as you say, there's a huge emphasis on shipping at the moment to try and decarbonize. There's a number of options to ship owners, one of which is slow steaming. Currently, that's seen as somewhat uneconomic. It's sort of counter to the idea of what shipping is all about, which is a service, a shipping service to supply transportation of goods and products that we all demand. And of course, it's very much a short-term solution. While slow steaming does indeed reduce the power of the ship, you've really got to think about what it does on a macro scale. And of course, ultimately, it will promote the requirement for new ships, new builds, and potentially early scrapping of perfectly good assets. This in itself produces environmental false economy because those activities as part of the life cycle of the ship are quite carbon intensive. The next thing that we can do is look for zero carbon fuels, which are expensive and of course less energy dense. So you've really got to think about how much storage you need to transport this without having to do numerous bunker operations. And similarly, they're perceived to be very far away on the commercial deployment. Likes of hydrogen, ammonia, and these sorts of these fuels are further away and probably most likely going to be deployed into land-based domestic purposes. The third, and what Armada believe, and I think what a lot of the shipping industry is really advocating for, is the retrofit of existing energy efficiency technologies. It's seen not just as a short-term solution. It's economic, but it's also an enabler of these future fuels. So they're fuel agnostic. They reduce the fuel consumption, and therefore this energy density challenge becomes less of a concern. And just finally, to pick up on your point at all of the cost of compliance, as we see these regulations come in, that is going to become more and more of a significant issue that ship owners have to grapple with. For Armada, the way that we see the industry at least having a strong interest in is hull air lubrication systems. We believe this is the case because it deals with frictional resistance quite simply. Frictional resistance is omnipresent. As long as the ship is upright and moving forward, you will get a component of frictional resistance, more for some vessels than others, but essentially it is there. It's a direct target that we can reduce fuel consumption and of course emissions from ship. So how do ALS work generally? What is the concept and what do we know? So it's well recognized that the injection of microbubbles or bubbles of various sizes within the boundary layer of the ship produce a reduction in viscosity of the seawater that's in that viscous sublayer of the boundary layer. That in itself reduces the net viscosity of the actual fluid surrounding the ship, and for that reason you experience a reduction in frictional resistance. Of course, less frictional resistance, less total resistance, less power to meet speed, or an increase in speed for the same power. Either of those effects ultimately result in a reducing fuel consumption and environmental emissions from shipping. The other lesser known or less marketed, let's say, phenomena that is going on within an air lubrication system, depending on how it's delivered, is there is a modification to the turbulence within the boundary layer, which in itself produces drag reduction effect. So the phenomena itself is multi-pronged. It's not just about introduction of air, but it's also about what influence that injection of air or air-water mixture, as the case may be, into the boundary layer that produces this double effect. I don't need to explain to anyone on the call why reducing drag is important. Of course, a reduction in drag, fuel and emissions is critical for the shipping industry as it develops over the coming decades. This very simple schematic is purely intended to give an indication of the different ALS categories that are currently on the market as of today. If I start from the bottom one here, you've got a fluidic lubrication system. This is basically the use of compressors to drive air down into bands at the bottom of the ship, and through fluidic oscillators and perforations on the trailing edge, you get the injection of air bubbles into the boundary layer. Cavity-based ALS is been around slightly longer. But essentially what you're doing is you're using a bank of air compressors to mechanically drive air down into cavities. There's a constant replenishment of that cavity, and it's the shearing effect between the water passing under the cavity and that air that sheds air into the boundary layer. For both of these systems, you of course need compressors on a continuous basis to generate that air lubrication effect. And for the cavity-based one, there is a lower speed limit, which is really fundamental. That once you get below a certain speed, that instability begins to diminish, and you don't get the same level of air lubrication. Where Armada is fundamentally different, it's sort of back to the drawing board in terms of how the design concept was developed. You'll notice the first interesting point is Armada takes water inboard of the ship and does that using the forward momentum of the ship. So we funnel water inboard, we pass it through a Venturi ejector, we produce an aerated mixture of air and water, and then we deliver an aerated mixture of water back underneath the ship within the boundary layer. The important factor here to really focus in is the Venturi and the ejector itself. That is a simple solid state nozzle. Water passes through it, and it's purely a matter of the Bernoulli's principle. You converge a flow given density and temperature the same on both sides of the Venturi. That convergence of flow increases speed. All that can possibly happen is a drop in pressure. So we designed the Venturi to produce a net suction of air rather than mechanically pushing air down using air compressors. And this is how we're what we term a passive air lubrication system. There's what the system looks like. A PALS, so passive ALS, is made up of a series of modular pods. Those pods look somewhat similar to the isometric drawing on the right hand side here. We incorporate an inlet box, and inside of this box you have basically a hydrodynamically favorable scoop. Nothing sits below the vessel baseline, but water is funneled into the scoop within here. That mates with this pipe. Water is funneled through the pipe down. This is the ejector. Inside of here you have the nozzle. This white line on top is the air line that draws in air from the deck level, or more conventionally we take from the bosun store, and we draw large quantities of air into the ejector. Downstream we have a diffuser which produces shear stresses that essentially tears that air into small bubbles, and then we inject an aerated mixture back through an outlet transition piece into the vessel boundary layer. The system itself is designed as a fully coupled system. So the inlet transition piece, the ejector, and the outlet is a coupled system. The shapes and sizes of these are designed in such a way that there is a dynamic imbalance between the inlet and outlet. That imbalance is designed to overcome any back pressure. So for instance, across this nozzle, but also provide a motive flow across the system. And that drives the ejector, pulls in the air, and that's how we achieve air lubrication passively. I'll skip on to the next slide. In terms of how this looks when it's integrated, at least from a design perspective, you'll see that these pods fit within frames and spaces that are pre-existing within the double bottom spaces. We create what we term PALS rooms. They're unmanned machinery spaces that we embed within the ballast tanks, and then we arrange the pods within those spaces. You'll see it takes a bit of a flocking bird arrangement as here. The design criteria is driven by computational fluid dynamics. It tells us where is the flow lamina coming into the inlet. We can fit as many units across the beam of the vessel as needed. The design criteria really that we only have to work to is that you can't have an outlet exhausting into an inlet. Otherwise, the Bernoulli's principle breaks down, because you get that aerated multi-phase flow through the Venturi, which would impact its efficiency. In terms of how we go about installing, I'll show more on the next slide, but we have an installation guidance manual that's been thoroughly, robustly reviewed by Armada, its third-party subcontractors, and also working in collaboration with the owners. What we tend to recommend is that you would crop an opening for this outlet transition piece insert plate. You tack weld this in place. you crop a hole for the inlet box, and then you feed the system in. You build the system up within the ballast tank space, and finally you raise this into space, tack weld, full pen weld, UT and coating. How that looks in practice, we, as you mentioned at the beginning of the call, we've recently finished the pilot deployment on an LNG carrier, 160,000 cubic meter LNG carrier in our partnership yard over in China, Yulian. This involved an installation of 14 units. As you can see here, these are the inlet boxes. So they've been raised into place, welded into place, and you can see the opening as the water will come into the system here as the vessel moves forward. So you've got an inlet, an inlet, an inlet, and then of course downstream of this you've got their corresponding outlets. If you were to go inside the space above here, you would see this, which are the insides of the inlet transition piece boxes. These flanges here are purely to enable galvanization and full pen welding in the inside of the boxes, so they're not inspection hatches for any purpose. They're just purely to ease in fabrication. You can see the isolation valves right here. Once the full installation is complete, you'll see it's actually I've purposely added this photograph because it's very difficult to even see the system because the integration is so seamless within the existing hull plating. So you can just about make out an inlet here. There's a corresponding outlet box here, here, and here, but it's very seamless as you can see within the existing hull envelope. If I provide just a bit more context, if I go back one slide, you'll see that we have flow control on both the water side and the air side, and we're able to pick up pressures and flow rates on both the water and air side. That's independent on each individual pod. So each individual pod is its own operating entity, meaning that we can control the amount of water, the amount of air, the delivered air to water ratio, and given the design of the diffuser, we can also control bubble size. That enables us to start doing fairly clever things when it comes to maximizing retention and managing the air carpet downstream in a higher sea state, for instance. Armada has a full automation system that sits over the top, so it's designed as what we call big green button technology. It's not designed to be requiring any sort of human intervention. We do provide HMI panels. In this case, we had one on the bridge, one in the ECR, and then one locally in the bosun's store, just for awareness of the guys on board the ship so they can monitor pressures and flow rates. So I'm assuming I'm getting close to time, so I'll close this one quite quickly, just as a roundup of what we believe to be the benefits of the Armada PALs. No compressors. Depending on the system that you're comparing against, that could result in a 30 to 50% increase in performance, assuming the same gross performance. We use the ship's more forward motion to create that passive air water mixture. Just in terms of this no compressors, we run about 10 kilowatts, which is control panel when the system's running in passive mode. That enables us to produce quite high results. So we're predicting double-digit fuel savings, which of course results in quick ROIs, anywhere from a year up to 7 years, depending on the utilization and fuel consumption of the ship. We're able to tune the air carpet downstream, so we can tune it more suitably to the speed, the draft, and of course the response amplitude of the vessel in a seaway. We target a flat operating curve, so instead of giving a single performance guarantee, we look to ensure performance is consistent when the system is on, it's working well, and you can run the system down to maneuvering speeds if that's what the owner desires. That's maintenance and breakdowns because less rotating equipment, and of course everything is embedded within the PAL spaces that we've created, so it's less intrusive to the vessel. And yeah, installation is quite simple. Just in terms of numbers, we installed on the blocks. So for any of the overboard hull intervention aspects of the installation, we did in under 7 days. So we believe that 7-day dry docking is possible for ships. So I'll leave it there, and very happy to take any questions at the appropriate time. But thank you.